So, Level 3 physicists, welcome back to the last lesson in the electromagnetism paper, electromagnetic induction. So in the last lesson we looked at forces on moving charges, in this particular case charges in a wire. What we discovered was that a current in a magnetic field experiences a force, and current is, also from our previous lessons, moving charges. So when a charge moves, it experiences a force. This doesn't just have to be a charge in a wire, it can also be a point charge, like an electron in a magnetic field. The equation is given by F equals QVB, where force is in newtons, Q is in charge in coulombs, V is the velocity of the charge in meters per second, and B is the magnetic field strength in Teslas. So what is the point of this generator effect that we've just discussed? Well, if a conducting wire cuts at right angles through a magnetic field, a voltage is induced across the ends of the conductor. Notice it has to be at right angles, for of course if it is parallel, there is no current being generated because it's not moving through the magnetic field lines. If the wire is part of a complete circuit, a current is induced or created in the wire. And here's a diagram here, so you have the wire moving up and down through the magnetic field at right angles, creating a current, be it negative or positive current depending on the direction of the wire. This is also known as electromagnetic induction. And what we do to work out what direction the current is induced, for instance, or what direction the movement is, up and down, or the direction of the magnetic field is another hand rule, this time Fleming's right hand rule, where the thumb is the movement of the wire up and down or side to side. The first finger is the direction of the field, and the second finger is the direction of the induced current. Remembering, of course, that the magnetic field always points from north to south, and the current direction is always from plus to minus. So the size of the induced voltage increases when either the speed of the wire going up and down increases, the strength of the magnetic field increases, or the length of the wire increases. And when I say the length of the wire, it's the length of the wire inside the magnetic field. So the equation for the induced voltage therefore is V equals little v BL, where V is voltage in volts from previous lessons. Little v is the velocity of the wire as it moves in and out of the magnetic field. B is the magnetic field strength in Teslas, and L is the length of the wire in the magnetic field. Not the entire length of the wire, it's the wire that's actually in the field itself. So here's another example where we use this time a solenoid, which increases the strength of the current and voltage being created. Because if a magnet is moved into a coil of a wire, a solenoid, a voltage is also induced across the ends of each of the coils. And if the direction of motion, or the polarity of the magnet, is reversed, then the direction of the induced voltage and induced current are also reversed. So we have something called alternating current. Currents going from positive to negative and negative to positive. The generator effect also occurs if the magnetic field stays stationary, so the bar magnet stays where it is, and the coil is moved up and down the magnet. So just as an aside, now let's look at the conservation of energy in electromagnetic induction. So the diagram we have here shows a metal rod moving to the right through a magnetic field, and the induced current in the rod flows as shown in the diagram. We know that currents in magnetic fields experience forces from previous lessons, so the force on the current is to the left, also shown on the diagram here. See, the opposing force. The force opposes the motion producing the current, and therefore work, which is of course force times distance, is done in order to sustain the motion. So if energy is to be conserved in the system, then the mechanical work done, force times distance, must equal the electrical energy that's being generated by the system. So let's the speed of the wire, say the v, velocity, and and the effective length inside the magnetic field be capital L. Then the induced voltage will of course be V equals little v BL, which we've gone through in previous slides. And we also know that power equals VI, so that means that the power on one side must equal VBLI. Okay, we're basically multiplying VB voltage, or substituting voltage into the equation on the right. The force on the magnetic field B makes on the current I is given by the formula F equals Bill, which is something we looked at in the earlier lessons. Okay, this force opposes the motion of the wire as it moves. Okay, so if the rod is to move at a constant speed, then the force sustaining the motion must be the same size, BIL. Therefore, the mechanical power equals force times velocity, which therefore must be equal to the electrical force times the voltage this time, and that must equal VBLI, because power has to be the same. We can clearly see therefore that the mechanical power, F times velocity, equals the electrical power produced, so the energy must be conserved in the system. Okay, so in terms of the utility of the generator effect, we create something called alternating current or AC generators. Most electricity in the world is produced using this generator effect, and the simplest generators and types are used in power stations all over the world to produce alternating current or AC, current that goes from positive to negative and then negative to positive. And here's an example of what AC means. So in the previous diagram we have the brushes, so it means that the voltage goes from positive to negative depending on the movement of, or the turn of the coil in the AC generator against the magnetic field. Of course it'll be zero here because it will be parallel, not perpendicular. So an AC generator can be considered to be like an electrical motor in reverse. As the coil is rotated, electromagnetic induction occurs. An alternating voltage is induced in the coil or created, as well as an alternating current. The alternating current is drawn off through the two ring slips we see in the diagram. And the faster the coil is rotated, the greater the amplitude of the voltage and the current, the larger in size it is, and also the higher the frequency of the alternating current, the more it jumps from being positive to negative current. So I'm just going to go through this diagram in a little bit more detail, labelling it as we go, so we have a greater understanding of what's happening. Okay, so I'm just going to label them with a few letters and go through the letters as we go. So in the first diagram we have here, the coil is rotating as shown in a magnetic field. Since AB is moving up and the right hand rule the generator applies, this shows us the induced current will be from A to B. Side CD is moving down and the wire, the current will flow from C to D. Since the current from this coil flows out of slip ring X, it follows because the charge carrier is positive that this slip ring will also be positive. Current flows back in at Y and this slip ring is negative. Right, so that's what happens when it's like that. So then, when it is at right angles and rotated 90 degrees, it arrives at the position shown here. In this position, no current is generated. This is because for this particular instant, the wires AB, which we're going to label here, and CD are not moving up or down. At this instant, their motion is horizontal, they're parallel to the magnetic field, and therefore no current is being generated. So finally, in this last kind of diagram we've got, notice the inversion of the letters. Okay, so A, B and C, D are now in different positions. though y and x are not. So after it's been rotated 180 degrees, it arrives at a position shown here in this last diagram. This situation looks like the first diagram, however, wire CD is now on the left and the current induced flows from D to C, and similarly for wire AB, the induced current flows this time from B to A. This is the reverse of the current direction in the first diagram. So slip ring X is now negative, while slip ring Y is now positive. Okay. Clearly, generators are very similar to electric motors. However, in generators, mechanical energy is converted to electrical energy, whereas in electrical motors, electrical energy is converted to mechanical energy. While the above generator produces a current that is alternating, it could be changed to create a DC generator, but this would require replacing the slip rings with something called a commutator. Thus, if we rotated it by hand, the simple DC motor earlier described in lessons would generate a direct current. And a final example of that is the bicycle generator. Okay, so in the bicycle generator, when the wheel turns, the magnet is made to rotate next to a fixed coil of wire, as you can see from the diagram, and electromagnetic induction occurs and an alternating voltage is induced, this time in the coil. This causes an alternating current to flow, so to the light bulb in the bicycle, and the bulb goes on.